Hi everyone, my name is Joan Pitarch and I'm going to talk about our work, which is called a new stochastic approach to the spread of environmental events enhanced by the wind. First of all, I'm going to start explaining the purpose of this work and the scheme of our model. The purpose of this work is to present a stochastic approach of the expansion of adverse environmental phenomena which are enhanced by the wind. For instance, a forest fire, the spread of some pest plants, among others. Okay. On the other hand, our model is based on the well-known susceptible infected recovered model, which is also known as the CMMSE model. At the same time, our model will follow a discrete scheme due to these two main aspects. The first one is that the temporary variable will be a natural number, so it will follow an iterative process. The other one is that the expansion takes place in a square grid with size n, where the cells represent an individual or even a group in the population under study. So our main goal consists in developing an adaptive neighborhood relationship and update criterion which will depend on the direction and intensity of the wind. Before explaining the model, I would like to talk about previous work. There are many papers which try to design this kind of models, but in our case, we want to point out the paper a multi-grid approximation to the expansion of Xylella fastidiosa in almond trees. Its authors developed their model using non-flexible and symmetric neighborhood relations. Some of these relations can be seen in this slide. Unfortunately, their simulations were all symmetric due to this neighborhood relation, and however, it's not common for environmental phenomena to be symmetric. Okay. Regarding our approach, we will only assume that the spread of our phenomenon moves in the same direction of the wind and takes advantage of its power to reach longer distances. Okay, and if we focus on the figure on the slide, it shows our approach in a simple way. The arrows refer to the direction of the wind, and the cells can be healthy in yellow, infected in red, and exposed for the next iteration in gray. Thus, given an infected element and some wind variables, let's determine the probability of infection of all healthy cells for the next iteration. About our neighborhood relation, it's clear that our aim is to obtain a function like the one we can see here. That is, given the intensity and direction of the wind, we want to obtain a square matrix of size n, where each of the entries refers to the probability of cell ij of being infected in the next generation. Okay. In this sense, the spread of the phenomenon also depends on the location of those infected in the previous iteration, and therefore the set of infected elements will be very important for us in order to calculate this kind of matrix. Okay. In this study, we only consider that the infected elements spread the phenomenon. Okay, from now on, let's suppose that the direction is in the first quadrant, and otherwise we will reason by symmetry. Thus, we can suppose it without loss of generality. Moreover, in the paper, everybody will be able to see all these kind of technical details. Okay. Once this is clear, given the direction of the wind and the infected element ij, we have to determine the probability values. Okay. To do that, we are going to use basic trigonometric functions such as tangent, cotangent, sinus, or cosinus. As we can see in table 1 on the slide, we will determine the values in a similar way as in polar coordinates. To sum up, the upper element I minus 1, j, will have sinus of theta as probability value. Okay, for I, j plus 1, cosinus of theta, and for I plus 1, j plus 1, the function f evaluated in theta. That is to say tangent or cotangent depending on the direction of the wind. Okay. Note that the function f is always positive and bounded by 1. Note that so far we have only used the direction. So the question is, how are we going to use the power of the wind in this model? Okay, firstly, we will do an arbitrary partition of interval 0, 1, and then we will have the interval divided in 4 parts. When the power value is in the first part, means that the wind doesn't have any effect on the spread of the phenomenon. So every element next to the infected element has the same probability of infection, okay? Otherwise, this power may extend the scope of the phenomenon for the following iteration in the same direction of the wind, okay? To carry out that, we're going to define a recurrence, which is called an enlargement process. As we can see in the slide, it only consists of expanding the number of non-zero rows and columns. So depending if our power is in the second, third or fourth part of the interval, there could be more or less cells that can be infected in the next step, okay? In this way, we allow the model to increase the scope and expansion of the phenomenon. In other words, the number of rows and columns to be added depends only on the power of the wind, in particular about which part of the partition they belong to. Moreover, we will set a constant c whose function is to adjust the probability of infection according to the distance to the infectious cell, okay? Finally, we have to do this process for every single element in the set of infected elements, and in order to obtain the neighborhood relationship, we will aggregate all these results, okay? Once we get the neighborhood relationship, we are going to establish an update criterion for our grid, okay? Firstly, let's suppose that the cell is healthy. Then, when the probability of infection is higher than the unity, due to this aggregation, this previous aggregation in the neighborhood relationship, this cell will be infected immediately. Otherwise, we will do a Bernoulli trial with each probability of infection, okay? Secondly, if our cell is infected, then we define a parameter delta, which indicates the number of steps in which the cell remains infectious, okay? After that, the cell dies. Lastly, cells that have died are not recovered, okay? Now, I'm going to show this process through an example, which, in my opinion, is the easiest way to understand it, okay? First of all, we denote healthy cells with 0, infected cells with 1, and dead cells with 2, okay? And the size of our square grid will be 5. As we can see in the slide, in the initial step, we only have one infected element. So the I subscribe 0 set only has one index, obviously. Let's suppose that we have p quarters as a direction, and given an arbitrary partition, we have the power of the wind in the second part of the interval, okay? So the value of m will be equal to 1. If we have the power in the first part of the partition, then m will be equal to 0, okay? Therefore, we have to reason as in table 1, and then we will obtain a neighborhood relationship like r over 0, as we can see in this slide, okay? Now we have to apply our update criterion, and we have to note that we are using delta subscribed ID like 1. Thus, we get 2 infected elements, and due to this delta, 1 dead cell, and the rest of the cells are healthy for some random seed. We want to point out that our model also depends on random seed values due to the Bernoulli trials, which are a random variable, okay? If we continue this example, it's clear that we have two indexes in the set of infected elements, okay? Therefore, we have to proceed for every single one as before. In this sense, we will get two matrices which will be added in order to obtain the neighborhood relationship for this step. Let's note that the direction of the wind is in the second quadrant, and then we are going to transport this angle to the first quadrant using its similar angle in the first quadrant. And moreover, the power is in the third part of our partition, so m will be equal to 2, and we will have to expand our matrix in order to get two non-zero rows and columns through our recurrence, where the constant c is 2, okay? After that, we will rotate this matrix using the second quadrant orientation, so we will get a matrix like the one we can see here. Finally, we will obtain R over 1 as a neighborhood relation, and then we apply our update criterion as we can see in this slide, okay? It's clear that we will get at least 4 infected elements and 3 dead cells for the next step, okay? In conclusion, I would like to point out that this model returns us non-symmetrical simulations, and if we change the seed value, we could obtain different estimates, okay? In addition, the set of parameters used could allow the model to be adjusted to the real data available. That's all, and thank you for your attention.